chair. Unless you want to stand up the whole time. Need to get your calculator. And also, this is the power supply, 5-volt power supply. It's not working on it. So I took it apart. It's fixed now. Y'all remember when we did the diagram. So this is what you see. This is the digital analog trainer. So it serves two functions for us. In the old days, we had a digital trainer and an analog trainer. We gave over $300 a piece for them. These guys here come around to, I think, $200 assembled, but you can get them in kit form too. You get them a lot cheaper. Of course, the power supplies we have on this is we have a we have a 5-volt power supply, right? Plus 5 volts. We have a plus 12. We have a minus 12, which is a blue one. And then up here we have two variable power supplies that will figure out what range they are. We'll actually go and calculate that. Now all this up here would be used when you take digital. Okay. So if we're going to measure these with our meter, this would be. So we have this is truly ground, by the way. This power supply is grounded. This power supply here is not. So this is an isolated power supply. Okay. But you can ground it if you want to. And I'll show you that in a minute. So you can represent ground, but you got to do it. You got to do it on the back. So here's our plus 5-volt power supply, and these are all regulated, by the way. So they're regulated power supplies. Now this guy here, we'd have to look and see what the current. So it's measuring 5.96, right? Which is pretty good. Here's our plus 12-volt supply, which is 11.8 volt. Here's our minus 12-volt power supply, which comes in at minus 11.9 volt. Now variable supplies, we still use the same common, or still use the same ground reference. But on these, to get to these power supplies, you have to wire them in with, so they don't have a banana plug jack. They just got a regular breadboard here, and you'll have to use your wires. So we got the adjustment for it is up here, right here, and we'll look at this, and we'll actually figure out what it's going to be. So that's what y'all see from this point of view. We also have some electronics on it that we're not getting into. So we do have a function generator on it where you can select a sine wave, a triangle wave, or a pulse waveform with this knob right here. This is where you set the multiplier on your frequency. This is where you do a coarse adjust on your frequency output. This is a fine adjust, and this is the offset here. So you still have the ability to do an offset like we do in our function. The only difference is the function generators that y'all be using actually has got it's actually two pieces of test equipment. It's got a frequency counter in there for you. Here's the schematic. It's got a frequency counter in there for you. Where this, you would have to use an external frequency counter, or you'd have to measure frequency with your oscilloscope. Now, when we look at it from the other point of view, this is what we see. This is where all the magic happens back here. And all we're really doing is looking at the power supplies. So what we got is y'all all got a copy of the schematic. This is y'all schematic, right? Understand? So the transformer. So I was looking at my schematic. I'll bring up the camera and point this stuff out on the inside. So here's a transformer right here. It's a multi-winding transformer. Some of them are center tapped. Okay, so this is the transformer. And then of course this connects to the main circuit board through a Molex connector right here. Okay. It's multi-winded though, and we'll look at that in a minute. And then of course, once we come in, we'll pull this off so we can get the transformer out of the way. is we come in and then we come through our rectifiers. So here's our two rectifiers right here. That's on the schematic. After we go through our rectifiers, we go through our filter capacitors, right? So we have, here's our filter capacitors. We have multiple filter capacitors because when we looked a little bit at the voltage regulators, some of the regulators themselves have to be filtered to take care of transient noise. So these little capacitors up here filtered for the regulators themselves. Here's two of the regulators right here. This is a 7912, which is a minus 12 volt regulator. This is a 7812, which is a positive 5 volt regulator. I'm sorry, a positive 12 volt regulator. We have two variable regulators, which are the 79. I'll get them up here. These are the LM337, which is a negative variable regulator, and an LM317, which is a positive variable voltage regulator. And this big guy out here, this is your 5 volt 3 amp supply back here. Okay, this is an LM3. Originally, we had an LM78H05, which was a high current version of the 7805, and it was in a TO3 case. We call this a TO3 case. And I'll give you all, I think there's a thing up on Blackboard that gives you all the case numbers and shows you the style. This gets bopped all the time, so we replaced this with a better version with an LM323, which is still a 5 volt 3 amp regulator. I'm sorry, this is a 5 volt 5 amp regulator. These are fixed regulators. So the regulators we run into is fixed regulators, which means they're going to regulate at a fixed value, kind of like a zener, or they're going to be a variable regulator that gives us the ability to set our output. Are you okay now? Now, when we look at this at the schematic, y'all looking at your schematic, first of all, we need to find our AC coming in, right? So here's our AC coming in. So this is where the power plug would actually be at right here. Okay, and this is the little switch you flip. This square means this is inside one unit. So what they've got is they've got a little neon bulb inside there. And that's what glows on the power switch when you turn it on. And this is all built in, so when you bought this, this side goes directly to the primary of the transformer. This other side of the switch comes through, and there's our fuse, right? You understand? And then there's our circuit for the primary of our transformer. Are you okay? This indicates it's an iron core transformer. And then here's our three windings. We have a center tap winding here. We have an untapped winding here, and then we have a center tap winding right there. So this guy's actually got 3 transformers. I can't see. I'll try to see what current they're rated at here for. Are we okay? And then, of course, these are the 2 little bridges that we looked at, bridge rectifiers. Now, this guy right here is a little different. Normally, when we look at that, that is a bridge rectifier, but the power supply is a center tap power supply. And what you got to watch out for is when you see a transformer and it's got a center tap and it's hooked to ground, that should tell you something. Now, if I was to come in up here and try to wire this, so we got 2 power supplies feeding off of that transformer. We've got the plus 12 volt supply and we got the minus 12 volt supply feeding off that one transformer. Okay, y'all understand? So if I was going to do it with nothing but diodes, then I would have to come up and do it something like this. So I would come off my transformer, and this would be, then I'm going to bring it out, and it would be a center tap, right? You understand? And over here, I would have these, and this would be my positive supply. We would connect them together, and then we would come over here, and this will go to our regulator. So this would be the 7820. And I'm not drawing all the circuitry. Okay. Then I would have to come in, and I would have to tap off these, and then I would come around and do like this. And then this would be one of my negatives. Oops, wrong way, Rich. Huh? Yeah, but I put my diodes in the wrong way. And what we're going to do, you see this done quite often with a power that's got plus and minus power supplies. So I'd have to come up here and I would do this. And now I'm going to point the cathodes here toward the transformer. So that would make this a positive power supply, right? And then back here, this would be my 7912. But if you notice the way these diodes are, is that if you look at this point right here, this one is looking at an anode, this one is looking at a cathode, right? And then when I look this one's looking at an anode, and this one's looking at a cathode. On this side, I have common cathodes. On this side, I have common anodes. Well, that's exactly what we get out of a bridge rectifier, right? You understand? So if I go back and look at this schematic, then what you notice is that here's a common cathodes. So here's common cathodes. Here, this is common anode. You know, see that? This sees a anode cathode. This sees an anode cathode. But notice, instead of one side being connected to common like we normally do, this side is feeding the what? The minus, and this side's feeding the plus. So what they did is they were, instead of trying to use these 4 diodes to get 2 power supplies, they just figured out how they could do it with an integrated bridge. So instead of having 4 diodes in there, what can they do now? Well, now what they can do is they can come up here and use a integrated bridge rectifier right here. I don't know if it's this one or this one. We have to figure it out. So one of them, the plus and minus, these are full wave center tap power supplies. Even though they use a bridge, they're using the bridge to 2 sets of diodes. That makes sense, you okay? And of course, this is all the filtering for this. In your data sheets, it'll explain that. And then this is the little LED that comes on. So this is a symbol for a light emitting diode. Sometimes they leave the circle off. And you got to forward bias it for it to light. So since this is a positive power supply, then we've got a what? We've got the anode pointing toward the positive and the cathode pointing towards 0. This resistor right here is to limit the current, of course, because once a diode is forward biased, it acts like almost a short, right? And this LED down here, of course, since this is a negative power supply, this LED right here is got the cathode pointing toward the negative and then the anode pointing toward common. So notice, neither side is positive and negative. One of them is setting at 0 volts and the other one is setting at something else, right? You understand? Do you understand that? And then these come over here, and these are the little terminal blocks that you hook up. There's your terminal. There's your banana plug terminal, and that's where you hook up to those. So these guys are real easy to troubleshoot. They tell you a lot. So if you turn it on and one of these LEDs don't come on, what do you know right off the bat? Power supply back. Yeah, power supply. If none of the LEDs come on when you turn on the switch, then what were the first place you'd look at? Right there at that what? I can't draw right there, sorry. Right there at the what? Right there at the fuse. So none of the LEDs come on when you turn on the power switch. What's the problem? Got to defect the fuse, right? Does that make sense? If one of them don't come on, like on that guy right there, these two LEDs came on. This one right here did. Right, you understand. So I didn't worry about the negative and positive power supply. I knew the power supply was working. I knew the fuse wasn't wrong because those two came on, right? Of course, this is really neat. This guy is set up for troubleshooting. These TPs, these are test points. So notice you got of course, you don't need a test point on the output because you got the terminals to measure, right? Yeah, I'm pointing here. But these are test points. Okay, I know I get it right. But see the test points up here? So what can you do with that choice point right there? Well, here you check the unregulated in, and then over on the terminal, you're checking the unregulated out, right? So just because the LED doesn't come on doesn't mean that the regulator's bad. So you need to say, okay, I don't have an output, so what do you need to do? Always check the input to the circuit. Because if you don't have any input, then you need the problem to be somewhere like a broke wire. It might even be the transformer. You understand that? Now the variable power supplies are a little different. And some of the things I don't like the way it's drawn. So that's the two fixed power supplies. I'm sorry, we got another fixed power supply down here. This is coming off this. Now this is a bridge circuit because there's no center tap. And see the big difference right there? So here, one of your sides is connected to common or ground. Up here, none of your bridge is connected to a common. So that's why that one turns that into a actually a center. Those two are center tap power supply. Come out of the bridge right here. This is a 4,700 microfarad capacitor. And then we go over here to what they're calling an LMH05. It was actually an LMH05. But we've changed these over. As they go out, we didn't get into the 78H05s. We went ahead and got the, what did I tell you? An LM323. So this guy's been changed out. And of course, unregulated in, here's regulated out. They got a post filter right there. This is the LED that comes on when the 5-volt supply is on. Then it taps up right here. There's your terminal right there for your 5-volt supply. And by the way, here's the ground terminal right there. Are y'all okay there? Not much to it. So this would be about all you would need to buy and build this thing. By the way, you can buy this in kit form, which will give you a good, I don't know if y'all don't know how to solder or not, but you can get this power supply in kit form for, I think it's $79, fully assembled, $40-something kit form. Not bad. If you go out and try to buy the parts, transformer is probably the most expensive thing that can cost. So that's a really, really good price. Plus gives you the advantage of building this thing. Everybody okay so far? Any questions? Now the variable power supplies. So here's my negative right here, right? This is going to come up, and it also branches over here and goes over to the LM337. Now this is a variable power supply. So this is a circuit that's actually doing the varying right here. So this is a potentiometer wired to act like a rheostat, right? That's what it is. So you don't run into many rheostats anymore because you got one device that can be wired to the, I can wire it as a potentiometer or I can wire it as a rheostat. So to wire a potentiometer to act like a rheostat, you just take what we call the wiper. So we refer to this guy right here as the wiper. And you just do what? You just jump it to one side. Okay, we okay? Everybody okay? So this is unregulated in, this is regulated out. This says minus 15, but we're going to calculate exactly what it is. Now, the LM317 and 370, these guys are identical to each other. It's just that one is a negative regulator, variable regulator, and the other one is a positive regulator. And y'all have the data sheets. I think it's, I know it's in the, if it's not on Blackboard, y'all need to let me know. But I do have a copy of it right here. So here's the LM317. This is the data sheet on it. Eventually. try this. Okay, so here we go. We got one of them. We'll close this up. Oh, that's the block diagram of it. But guarantee there's a zinger in there somewhere, right? So what we're looking for is this gives us the operating temperature. We'll come back and look at these later on. The line regulation. So what's the line regulation on this? You'll see. So line regulation is from the input, right? Y'all understand? So line regulation would be this guy right here. And then load regulation would be, where's the output? Oh, wrong one. The load regulation would be right there. So this would be what they call line regulation right here. Oops. So this has a load regulation. It depends on what you're looking at. 25 degrees centigrade with the guy dropping about 40 volts, 3 to 40 volts, and it's going to be within 0.01, 0.04, typically 0.01% to 0.04. Load regulation depends on what your output is. Could be anywhere from what. This is 25 millivolts. I'd have to figure this out, guys. That says what? 25 millivolts percent per V out. So we'd have to figure that out. This is how much the adjustment pin takes. So normally we don't, when we calculate the thing, we don't get concerned with the adjustable pin because it's only pulling what? Typically what? 3 microamps. Now this is what concerns us right here. This is what they call the reference voltage. Can y'all see what the reference voltage is? It can be anywhere from 1.2 volts to 1.3 volts. But normally when we do our calculations, which one would you think we would use? So we got 3 columns. We got one called minimum, we got one called typical, we got one called max. So what would y'all think we would use? No, we use the typical. Yeah, because we're not going to be there anyway. So we'll use a typical to calculate. But what it's going to do is it's going to give us, if we're trying to design it, we're going to say, okay, what do I want out? What do I want out? What am I putting in? What do I want to put out? So if I wanted a 15-volt variable supply, then we'll calculate the size of the resistors, and then we'll choose the standard value, right? First of all, we'd choose a standard pot, because we choose a standard pot, and then we would calculate the other resistor, and we'd get what we could get. Okay, y'all understand? So the 1.25 works out really, really well. And you can see that. We'll actually measure that too. Long-term stability, that's pretty neat. And these curves are very impressive, but we usually don't use them. But this is the setup right here. So we're going to have a rheostat right here. Let's see if we zoom in. But normally we don't use rheostats anymore. We use what? Yeah, wired active rheostats. And then we're going to choose an R1. So this is, where'd I go? Okay. So then what I'm going to do is I'm going to choose an R1 that would give me, what did they say that adjustable voltage was right here? So this guy right here, the way this thing works is R1 always drops 1.25 volts. So that means the output would be, always would be 1.25 volts more than what you set right here. So even when I adjust this pot all the way down to 0, the lowest we can get out of this thing is 1.25 volts, or close to it. And then what I started doing is I started adjusting this, right? You understand? And when I raise this voltage right here, what's this voltage right here going to do? So if I have this at 1 volt, what's this volt right here? What's this voltage right here going to be? Huh? Well, it's going to be whatever I put right here plus 1.25. So it's going to be 3.25, right? You understand? This resistor right here always drops, if it's regulating, this resistor always drops about 1.25 volts. So what that means is if I come over here and set this right here to 5 volts, right here, what would the output voltage be? If I set this point right here to 5 volts, what would the output voltage be? 6.25. That's exactly right. But it's going to be regulated. Because if this voltage tries to go up, this voltage will try to go up, right? And the regulator is going to cut it down. If this voltage tries to go down, this voltage over here will try to go down, and the regulator would do what? Would adjust it back up. So if I was to come up here and if I'm going to design and use this thing, which is it's real easy to design around. So y'all help me. See if y'all can figure out. Because this guy is real easy to design around, and it's very easy to make a variable power supply. I'm not going to draw the filters. So we got this resistor right here, right? You understand? And then we've got this resistor right here. So the first thing we would do is we'd use a standard pot. What standard pot do y'all think we got? What do you want to use? Huh? That's big. That's big too. Let's choose a smaller one. 10K. So let's use a 10K. This is a very standard pot. Okay, since it's a pot, we're going to come over and do this, right? You understand? Okay. Now what we're going to do? Well, we're going to choose a current that we want this thing to run at. We don't want to exceed the rating of the pot, but we don't want the current to be real high. So let's choose like 5 milliamps. Which is well, so I could use a pretty small pot right there, right? Okay. So what do we want to regulate at? So what output do we want to regulate at? Give me one. Okay, so let's say we want to regulate at 5 volts. So when that pot is turned all the way up, let's see if we can do this. So we chose a 10K pot. Let's do this backwards. I'm sorry. I got away from myself. So we're not going to choose a pot. We'll have to choose. So let's do it this way. So we want 5 volts. So if I want 5 volts, what would this point right here be to adjust this up to 5 volts? It's going to be 5 volts minus 1.25, right? Okay. 3.75? Okay. So 3.75. And what size pot did we choose? We chose a 10K pot. Okay. So first of all, now I got to come up and I've got to find out what current that's going to be. So that means to get this guy right here to drop 3.75 volts, 3.75 volts at 10K, that's when it's maximum. We got to turn it all the way up. What would the current be? Okay, 375 microamps. So odds are we'd want a little more current than that because we want to get more current flow to the pot. Okay, so now I know this is a series circuit we're going to ignore the current flow into the adjuster because it's only like 5 microamps, right? You understand that? So I'm going to choose a resistor that's going to drop 1.25 volts at 375 microamps. Y'all see what we're doing? What laws are we using here? Ohm's law. But all I need to know is this resistor right here is going to drop what? 1.25 volts. And then I go from there. I choose a standard pot, right? You understand. I calculate the current. So I take 5 volts minus 1.25 volts. I use that to calculate the current. Now I'm using that current since this is a series circuit. And what's constant in a series circuit? Current, right? And I'm going to calculate the size of resistor that will drop 1.25 volts at 375 microamps. 3.3K, that worked out great. Huh? Why did you calculate that? Huh? What's that? What did you calculate? 375 microamps. What did we get? Oh, that is a standard value. Okay, I didn't understand that. When you said it's a standard value, I thought you rounded to a standard value. If it don't come up to a standard value, if you choose a size that's smaller, then you'll get more than 5 volts out. If you choose the size, if you choose the size that's bigger, you get less, right? You understand? If you choose the size that's smaller, you get more. Normally, we see more. Okay, let's look at our schematics and see what we should be able to adjust this power supply to. It says 15 volts. So right now, if I was to troubleshoot this and it said 15 volts, I'd say I got a problem. So what size are we using? So this feedback resistor right here, what size is it? Y'all see it on the schematics? Not 2K.
RS 120.
R5.
R5.
Or R4. We're doing the positive. R4. What's R4? Okay, so that's 120 ohms. Okay. Are you okay so far? Alright. And then what size pot are they using?
2K.
So they're using a 2K pot. Y'all follow me so far? Yes or no?
Where'd you get the
I measured it. It was on the schematic.
I see it.
Yeah. So when you look at the schematic, what we're doing is we're down in here. So here's my feed. This is the feedback resistor right there. That's the one that's actually sensing. We're on the wrong. I'm up here. So it's what? 120 ohms. And here's the pot wired as a rheostat. So when I draw it, I'm drawing it like the schematic over there. So I'm drawing it right like this, right? Yeah, I'm not there yet. I just erased my whole thing, which is par for the course. So here's unregulated in. Here's regulated out. Here's my feedback resistor. It's 120 ohms. Then here's my adjust. This drops down to 2K. And then we have a pot that's wired as a rheostat, right? Okay, guys, where do I need to start at? Well, I know, yeah, well, let's see if we can do that. Well, I know if I adjust this pot all the way down here, this goes to 0 volts. Right, you understand? So what voltage would I have up here? So if I got 0 volts right there, what voltage would I have right there? Huh? Can't have 0 right there. That resistor will always drop 1.25 volts. No, say one. All right. So it's always going to drop 1.25 volts. Okay, y'all understand that? So what can I do now? If I know this resistor is 120 ohms, I know it's dropping 1.25 volts.
then I can come up here and I can say, okay, what would be it? Whatever current flows through this is the same current flow through that, right? You understand that? So I'm going to divide this by 120, and what current did we get? What's that? Is everybody in agreement there? Okay. Then I'm going to take that 10.4 millivolt, and I'm going to come over here, and I'm going to see what a 2K resistor will drop. Okay, y'all understand that? So I'm going to come over and say V across that resistor, I don't know the number, would be equal to what? 10.4 milli times 2K. So what we got? What's that? 20.8? Are you okay? Okay, so what should we be able to adjust this up to? Plus what? 22.1. Okay. So that's quite a big. That's quite a bit different than 15 volts. Let's see if how y'all calculate this. Let's see how good we are. So I'm gonna hook this back up. I'm gonna come over here and we'll turn it on, right? We're looking at the positive regulator, so I'm gonna hook my meter up. Okay. Turn it on. So there's 1.26. We use 1.25, so I've got it turned all the way down. And I'm going to hover up here and I'm going to turn it all the way up. And it goes up 20. We don't quite get 21, but we got 20.04. Huh? Yeah, but I got this guy right here probably, this guy right here is dropping 1.28. So when they said 1.25, that was just kind of a rounded thing, but it's still, the calculations still worked out perfect, right? So this has got to be. So when we said 15 volts, it said, no, we got 20 volts. See the way we calculate that? You see how you can figure that out? So what you would do is you'd probably use a resistor around this range right here, maybe no more than 5K. Then 5K. And then what do? Well, you say, well, I want this guy to drop. If you want a 20 volt regulator, then what you would do is you'd say, okay, I want to, this guy right here is going to, right? I'm going to plug my power supply. I've been letting my battery, I need to do that every once in a while, right? Let the batteries run down. It's been a while since I did it. So guys, these guys are available online, LM320, LM317s, LM323s, you know, all these are available online. Transformers are available online, or you could do what? If you wanted to build your own power supply, odds are it would probably be better to buy the kit and put it together. So these are the power supplies. One more thing we need to look at. When we do our power supplies, we're going to be using this transformer right here on the trainer. And it is ground isolated. It is not connected to ground. Keep choosing the wrong thing. So it's a 12.6 volt center tap transformer. It's kind of labeled kind of funny. The trainers label it 6.3 center tap 6.3, right? You understand that? That's the way it's labeled on the trainer, but it's actually a 12.6 volt center tap transformer. It's not grounded. So what that means is when you build your power supplies and you're trying to make your voltage measurements, well, what are you not going to use? You're not going to use this ground. If you use this ground, then all your measurements are going to be wrong. What you'll do is on your power supplies, it'll indicate what's supposed to be common, right? You'll use that as the common. So this is the transformer. Here it is right here. It's right beside the the adjustable power supplies. So here's our 12.6 center tap ungrounded transformer. So just because the primary is grounded, once you go through a transformer, if you don't bring the ground on the other side, then transformers couple magnetically, right? You understand that? So that's why they have to reground your side of your house. So that's why they bring that down drop down into your house and comes into your meter. You'll see a copper wire coming back and reestablishing ground on the secondary side of the transformer. So I got any questions on this? Pretty straightforward power supplies. These are still linear power supplies. What we'll do next class is I'll show y'all basically a switching power supply, which is what most of our computers use. So linear power supplies are easier to troubleshoot. They're easier to design. They're real simple to troubleshoot. Switching power supplies, when they go bad, you don't know. In fact, your computer power supplies are not repairable anyway. If you ever broke that plastic box off, you'd see that's encapsulated in a big chunk of epoxy. You can't fix those things. The little bricks you get to charge your phone, those are switching power supplies, but those are not repairable. So if you ever broke them apart, open them up and see a big old box of epoxy, by the time you've done all that out, it's good. Yeah, then it's all done by an integrated circuit too, which is probably proprietary, which you wouldn't be able to fix. Switching power supplies, normally what we do on a switching power supply is we just replace it with a linear power supply, which is what we're doing here. It goes bad. These guys are very troublesome. They're easy to do. Somebody say this. These are the power supplies on this guy. Unfortunately, we don't have a schematic, but it's very similar. Put out by the same company. So they don't use a integrated circuit. So these are the rectifiers up there. Let's see them. Looks like it's got a couple of sets. What are these? These are our filter capacitors, right? Here's our two potentiometers right here. These are wired from it. And all your regulators are back here on the heatsink. And what's a heatsink, guys? Yeah, normally when they make devices, they're trying to make them as small as they possibly can make them. So, device by itself will not be able to dissipate the heat that it's supposed to generate. Just about all solid-state devices, if you're going to make them run at their specified power dissipation, you're going to have to do separate little time frames. So a lot of times you can use the chassis itself. So if you look at these regulators, they're actually hooked up to the chassis themselves. This is a thermal insulator, which means it's got very, very low resistance to heat, but it's got real high resistance to electricity. You can get a mica, and then if you use some of the other ones, then you have to use what we call a heat sink compound that you put on there as a paste. I'll show y'all that. If you buy these little rubber ones like this, then you don't have to put anything in there. So what this does is it allows the heat transferred in the regulator, make it to this metal cage. But this is the whole metal cage, right? You understand? This guy didn't have enough surface area, so they literally used what we call heat sinks. Heat sinks are just to increase the surface area and make the size smaller. What they do, these heat sinks have these vanes in them. See that? And when you mount these things, you're supposed to mount these things vertical. You'll understand why. Because they dissipate heat by convection. So when these things heats up, what happens to air when it gets hot? It rises, right? And what would that do? That would automatically pull cold air from the bottom. If the heat sinks are not mounted like that, normally we put fans on them or something like that. So if you ever look inside your processor, it's going to have a fan on it because the heat sink on that thing is mounted horizontal. So these are used to increase the surface area. So this whole thing right here would be the surface that's dissipating the heat for those regulators that are on the inside. But you got to isolate them, right? Understand? This is heat sink compound, by the way. I can see if I can get it here. So it's a paste. Used to go buy it at Radio Shack, but I heard Radio Shack's fixing to fire with 5 by clubs. No, they're not. They're still around. Yeah. I think there's still one over at home. But this has got a Michael washer behind it. Now, Michael washers transfer heat, but they're really good insulators. But the problem is it doesn't have that rubber surface. It would contour with the 2-metal surface real good, right? You understand? When I put metal against metal or metal on solids, then you don't get a real good. You get all these gaps in here. So what we do is we fill in the gaps with this paste. It's called heat sink compound or heat sink paste. Odds are now you'd have to order it online. I know Ford Distributors is still in business up in Birmingham on 4th Avenue South. Right on the left there, you get on the interstate before you get to Regent's Park down there. It's on the left. You have to turn back to the left before you get to where you can see the park. So you don't want to mount these things directly on the metal because this metal tab right here is electrically hot. This is usually the regulated out right here. So if you're going to work on these things, don't wipe that paste off. If you don't have the paste, if you take it off, don't wipe the paste off. Right? Of course, if you replace it, you need to buy that paste and put it on there to get a real good transfer of heat between the metal tab on the regulator and then the metal surface that you can see.
Should you increase the size of them?
Yeah, you can, but the bigger the size, and there's calculations, by the way. So heat sinks have what they call a thermal resistance ratio. And you can buy heat sinks, or if you got a milling machine, you can make it yourself. You don't want to use a heat sink that's too big because it's not going to help you get more power out of the transistor, understand? Or out of the transistor that. And the problem is the bigger the heat sink, the more space they will occupy. But yeah, using a heat sink too big, it's not going to hurt you. It's just going to cost you more. Using a heat sink that's too small would definitely might cause you problems. So when you get into the data sheet for these guys, it'll give you. When you get into the data sheet for these guys, it'll give you what you need to do to calculate the heat sink you're going to put. So here's the LM337 again. So there's our negative variable regulator. This is the this is the LM317. This is the positive variable regulator. And here's your 7805s. And we don't have the schematic on it. So I'm not sure how they get 3 amps out of a regulator that's only rated. I think what they've done is they've got to put them parallel. And then they put these little old small resistors down here. This is to make them share the load. And I can't tell you that. That's just me talking from power supplies that I worked on. So they got these high wattage resistors right here. They don't show up real well. So the 2-watt resistors, you'll see them. And they've got 2 of them. So a lot of times what we can do is we can put a real small resistor in series with the 2 devices. And if one of them tries to take the load, then it'll automatically fold by. But I'm not saying that's what it is. Pretty standard. We could figure this out. It would just take a little while. I've been looking up trying to get these 2 things are made by the same company. This one they gave us all the schematics on. This we didn't do anything. And I can't find any schematics on this online. It would be nice if we had one because it would make it easier to troubleshoot. Questions? Yeah, like these guys, you don't have to use the heatsink compound on these rubberized devices because they're rubber and they'll contour those surfaces really well. All right, any questions? I know I've ripped off somebody's lap. We're going to go to lab.
Oh,